So today we are starting trigonometry. And trigonometry, the definition of trigonometry is literally angle measurement. So the Greeks were some of the founders of trigonometry, and that goes along with they had some of the most aesthetically pleasing architecture in earlier times. So trigonometry literally means angle measure, and we base trigonometry on the unit circle in our coordinate system. So we still have our quadrants 1, 2, 3, and 4. But what's different from what you learned about angles in geometry is that we can have, of course we have positive angles like we would normally. Positive angles are measured, we go this direction. But we can also have negative angles. And we can also have angles that are bigger than 180 degrees. We can have angles that are 360. We can have angles that are 1,000. And no, we haven't seen the Winter Olympics in a couple of years. In the Winter Olympics, they have the competition, I believe it's called the pipe competition, where they do several turns riding what would look like a skateboard. It's not really a fancier term than that. And the number of turns that they do, they are often multiples of 360. And that's just one simple example of how angles can be bigger than 360. Okay, so first of all, theta, because the Greeks were some of the foundations, many variables in trigonometry use Greek letters. So theta is one of the most commonly used variables to represent an angle. So as I'm saying, theta can go from negative infinity to infinity. All right, so we know that one way that you measure angles is with degrees. So let's name the quadrants, because location is going to be a theme. Let's name the quadrants in which these are located. So let's take a look here at 420 degrees. 420 degrees. Well, we know if we go around one time, that's 360. 360 plus 60 is 420. So that puts us in quadrant 1. Okay, negative 150. So we know if we go this direction, all right, from here to here would be negative 90 plus a negative 60. That would be negative 150, and that would put us in quadrant 3. All right, 135. We know we would go this direction. Here to here is 90. 90 plus 45 is 135. So that would be quadrant 2. And how about 1,020? Okay, 1,020. So we know that one rotation is 360 degrees. So we could think about multiples of 360. If I go around twice, that's 720. So if I take 1,020 minus 720, that's 300 degrees. So where's 300 degrees? Well, from here is 90, 180, 270, plus 300. That would be quadrant 4. Okay, so if you were looking at your notes, in example 1, I told you to go to one of your unit circle pages, or you could have just written this on a piece of notebook paper. Okay, so if you're looking at your guided notes, in example 2, I talk about degrees being broken down. So in geometry, if you actually use protractors, or if you did like a protractor online, you know that angles don't always land up perfectly on a nice degree. So let's talk about that. Something I probably should have said earlier. We know that this is our origin, and we know an angle is made of 2 rays, and we know that the ray that lies on the positive x-axis, that's called the initial, which means the starting, and the side where that rotates as you change the side of the angle is called the terminal. So initial side and terminal side. Okay, so we know that when we're measuring angles that the terminal side does not always land perfectly right on that tick mark. So just like yards can be broken down into feet and inches, or meters can be broken down into centimeters and meters, degrees can be broken down into minutes and seconds. All right, and not a surprise, if we think about minutes and seconds, we think about time. Time is based on circles. All right, and doing some history back on what would be, I don't know if you call the sundial. All right, trigonometry is based on a circle, so that's why it goes along with that 1 degree can be broken down into 60 minutes. and 1 minute can be broken down into 60 seconds. Okay, so just like in many conversions, you have to be able to go back and forth. All right, so writing an angle in degrees, minutes, and seconds is like the pretty version of the angle, but working with it, you actually need to put it back to degrees, or in other words, degrees with a decimal. So how would I change 120 degrees, 46 minutes, and 19 seconds to just degrees? All right, so I know I have my 120 degrees. Since there are 60 minutes in a degree, I would take 46 divided by 60. And since there are 60 seconds in a minute and 60 minutes in a degree, 60 times 60 is 3,600. I would take 19 over 3,600. So if I take 120 plus this, I always take it out 4 places since we're going to degrees, minutes, and seconds. This would be 120 degrees, 120.7719 degrees. Now, I always want you to be thinking about location. This would be in quadrant 2. Okay, how about the next one? All right, we have negative 36 degrees and 58 seconds. All right, so first of all, the negative is just telling me that it's going to be in quadrant 4, as I showed you here. I'm going to put that out to the side. If I'm changing this to just degrees, getting rid of the minutes and seconds, I would say 36 plus, this is seconds, so it'd be 58 over 3,600, which means negative 36.0161 degrees. Okay, now how about going the other way? So it's kind of like going back to fractions that, you know, if you get a fraction, you need to reduce it, put it in the finalized version. So let's say that you had this angle in degrees and I wanted you to put it in degrees, minutes, and seconds. Also the directions in example 3, just to review some geometry, because trigonometry is based on a lot of geometry. I'm going to ask you to find the complement and the supplement. So first of all, how would I change this? Well, this is the part that I need to change. Well, if you think about when we were going the other direction, we were dividing by 60. So that's why we are going to take the 0.6045 and multiply by 60. And that's going to give me 36.27. Okay, well, I round it a little bit. So then 36, since I multiplied by 60, that's your minutes. So then what's left over is your seconds. Now, we do not multiply by 3,600. Let's think about why. You took this entire number and multiplied by 60. You multiply by 60 again, you've essentially now multiplied this number by 3,600. So that's why it's 0.27 times 60, which is 16. So that would be 75 degrees, 36 minutes, and 16 seconds. Now, how do I find the complement and the supplement? Okay, the complement, we know, are 2 angles that add up to 90 degrees. So I'm going to have to take 90 and subtract. All right, so now, unlike we always think of a base of 10, we're going to be thinking of 60. So I have to borrow 1 degree, so 89 degrees is 60 minutes, and I have to borrow a minute to get seconds. So the 60 becomes 59, and now I have 60 seconds. So the complement of 75 degrees, 36 minutes, and 16 seconds is 14 degrees, 23 minutes, and 44 seconds. Now, how about the supplement? Remember, supplements are 2 angles that add to 180. So again, I'm going to have to take 180 minus this, and we have to be thinking about terms of 60, okay? I have to borrow a degree. All right, I have to borrow a degree, and so this is going to become 179 degrees. Okay, and then I have to borrow a minute, so 60 becomes 59, and 1 minute is 60 seconds. So that ends up giving me 140 degrees, 23 minutes, and 44 seconds for the supplement. Okay, so degrees can be broken down into minutes and seconds. The supplement and complement was just to review some geometry, since trigonometry is based on geometry. Now, here is something that is a foundation of trigonometry. Okay, angles can be measured in both degrees and radians. Now let's talk about why do we have to have radians, because radians actually end up being more useful than degrees. Let's think why. If I draw, and yes, these are sad circles, if I draw all 3 of these circles, they do not look congruent or the same, but aren't they all 360 degrees? Okay, if I look at these three, yes, they're all 360 degrees, but don't they have a different circumference? Okay, so radians measure arc length. So when I'm talking about arc length, when I say circumference, that is like the arc length of the entire circle. So here's the deal. Think about if I should have just got this out for you, if I had a piece of string. I can wrap that around a circle, take that out, and actually measure it with a ruler. So radians can measure length and distances. So let's think about the Earth. Our entire GPS, grid system, everything that operates everything we do now is based on a circular grid system. So we have to find lengths, for example, between cities, and our Earth is round, I know, shocker. And so that is why radians can be more useful. Okay, so more conversions. Before I do that. So just to give you a visual here, if I have a circle and an angle, how do I figure out measurements? Okay, well, an angle is found by taking the arc length divided by the radius, or you could say arc length equals r times theta. All right, just like you know basic formulas like distance equals rate times time, we need to know arc length equals radius of the circle times theta. Okay, so now we have to be able to go back and forth between degrees and radians. Now I want you to understand why we do what we do here. So if we know that all circles have a 360 degrees, and we know that the circumference of a circle is 2 pi r. Now, I didn't emphasize this, but I said that trigonometry is based on the unit circle. If it's based on a unit circle, whatever that unit is, meaning inches, centimeters, feet, yards, miles, whatever that unit circle is being measured in, the radius is one of that unit. Okay, so that is going to help us then take and go back and forth from degrees and radians to degrees. Okay, so if I have 360 degrees, we know that equals 2 pi r, because isn't that distance around? Okay, so now I know r is equal to 1 because this is based on a unit circle, whatever that unit is. Now, if I divide both sides by 2 pi, which I can because it's an equation, that tells me that 180 over pi equals 1 radian. So what does that mean? That means when I'm taking an angle from radians to degrees, I'm going to multiply by 180 over pi. Okay, now let's go the other way. Again, 360 degrees, that's all the way around the circle, 2 pi r, all the way around the circle. Radius of a unit circle, whatever that unit is 1. Now, if I divide by 360, I get 1 degree equals pi over 180. So this is what I'm going to use when I'm changing degrees to radians. Okay, so let's go to example 4. Let's convert these. And also, let's just go ahead and get in the habit of naming where these are. So 150 degrees, I want you to change that to degrees. So I'm going to multiply by pi over 180. The zeros reduce. 15 and 18 reduced by 3, so we get 5 pi over 6, and that is in quadrant 2. Now, if we have nice whole numbers in my numerator and denominator, we want to keep our angles in radians with pi. Saying that, let's go to B. I have 321.12 degrees, all right? So if I multiply this out, this is not a nice whole number, it's not going to reduce. So unless I have a nice fraction like this, all right, we're going to go ahead and multiply out pi and divide by 180. So I get 5.6046 radians, which is in quadrant 4. Okay, in C, I have negative 75.64 degrees. That's in quadrant 4 as well. I'm going to change that to radians. This is not going to reduce like a nice whole number in 4A. So I am going to have to just multiply this out by pi, divide by 180, and I get negative 1.3202 radians. Okay, now let's go the other way. Let's change the radians to degrees. All right, so think about this. If you're going from radians to degrees and you have a nice radian measure to begin with where it's not a decimal, you think about this. If you get mixed up, don't you want your pi's to reduce? So that's a way to keep track. I'm going to be multiplying by 180 over pi. So my pi's reduced. 3 goes into 180 60 times. So 60 degrees is the same thing as pi over 3. That is in quadrant 1. Okay, negative 2 pi over 3 multiplied by 180 over pi. My pi is reduced. 3 goes into 180 60 times. We get negative 120 degrees, which is quadrant 3. Now, take a look at C. Do you notice I do not have pi in that? So that just meant that it's not going to be a nice whole degree. All right, so that means we're going to end up with a decimal, which means we're going to have degrees, minutes, and seconds. So when you see 1.7, that doesn't mean it's in degrees. That means it's in radians because there's no degree symbol. So I'm going to multiply by pi 180 over pi. I'm going to multiply that out, and I got 97.4028 degrees. All right, that's fine. That's in quadrant 2. Let's practice what we did earlier. Let's change that to degrees, minutes, and seconds. So I'm going to multiply 0.4028 times 60, and that's going to give me 24 minutes. And then whatever was the decimal, I'm going to multiply by 60 again, and that's going to give me 10 seconds. So there are more notes on that, but we're going to continue that for tomorrow. So now what I want you to do for tomorrow is I want you to take your unit circles, and if you need to stop this to write this down, or you may have it, I want you to go around the unit circle and put down all these angle measures, 30, 45, 60, 90, 120, 135, 150, etc. And I want you to convert all of these to radians. These will be nice fractions with pi. Then I want you to take the rest of the unit circles. I purposely have divided these up and multiples of 45. Okay, turn the page. And you will understand why I'm doing this in this way. If you notice, all of these are 30 degrees away from the x-axis. So 30, 150, 210, 330. And then these are all 60 degrees away from the x-axis. 60, 120, 240, and 300. Okay, so I need you to do these mindfully because not only do I want you to fill this out, but I need you to look for patterns. You need to look for patterns as far as what's true about what would be considered the quadrantal angles, in other words, the angles on the x and y axes. What pattern do you see with these multiples of 45? What pattern do you see with these that are 30 degrees away from the x-axis? What patterns do you see with these? Because within a couple of days, we're going to be doing a quick quiz during our Google Meets or in class if you're somebody who attends. And you're going to have to write these down from memory without reducing. So start looking for patterns. Start thinking about ways to remember these. Making flashcards may be helpful as well.